We engineer our concrete bridges to withstand the predictable pounding of heavy semi-trucks, but the forces of gravity and traffic are manageable. The actual structural threat tearing these massive spans apart is hanging right above them. Every massive concrete structure acts as a giant thermal battery. Throughout the day, the concrete absorbs immense amounts of radiant energy from the sun, storing that heat deep within its core. This chart illustrates the 24-hour thermal equilibrium cycle engineers historically relied on. During the day, the bridge absorbs energy and heats up, but at night, the cool ambient air acts as a critical reset mechanism, draining the absorbed heat out of the concrete and returning the structure to a neutral state. The entire mathematical foundation keeping modern infrastructure standing safely is built on the strict assumption that this nightly thermal reset will always occur. In this dual line graph comparing historical global temperature increases, a critical divergence appears. The bottom line shows daytime temperatures rising steadily, but the top line shows nighttime temperatures surging upward much more aggressively, closing the historical gap between day and night. As that gap closes, the structure's cooling window physically shrinks to zero. Massive concrete blocks no longer have the cold air necessary to shed their accumulated daily heat before the sun rises the very next morning. The heat simply carries over. The bridge is forced into the next day's heating cycle before it has recovered from the last, locking the concrete in a perpetual, compounding state of thermal stress. The specific climate conditions these massive spans were engineered to survive no longer exist. Our infrastructure is running out of time to cool down. To see the damage this compounding heat causes, we have to look inside the materials. Concrete has poor thermal conductivity, making it act like a massive thermal sponge. This creates a non-linear temperature gradient. The sun superheats the surface asphalt and the top layer of concrete, while the thick interior core and the steel girders beneath remain shielded and cool. Physics dictates that hot materials expand. The blistering top layer of the bridge aggressively stretches outward, but the massive, rigid bottom layer refuses to move, physically resisting that expansion and forcing the entire deck to warp upwards. The extreme density of the bridge traps the destructive energy of the sun deep within its own core. The structure is now in a state of internal war. The conflict gets even more violent at the microscopic level, right where the embedded steel rebar grips the surrounding concrete. Steel and concrete process thermal energy at different rates. Steel elongates at roughly 6.5 microstrain per degree Fahrenheit, while concrete only expands at about 5.5 microstrain. When encased inside concrete and subjected to compounding heat, the faster expanding steel generates self-equilibrating forces called eigenstresses. The steel is violently pushing against the rigid concrete shell meant to protect it. These hidden internal eigenstresses can exceed 300 pounds per square inch of tensile force. That is 3 times stronger than the absolute maximum live traffic load the bridge was designed to hold. You could remove every single car from the highway. Without the nightly cooling reset, these materials are inherently incompatible, tearing each other apart from the inside out simply by existing in the sun. When you multiply that microscopic friction across thousands of tons of material, the physical shape of the entire bridge begins to contort. Engineers install expansion joints between concrete segments to act as mechanical pressure valves, giving the structure a gap to safely expand into during the heat of the day. But intense, compounding heat accelerates material deterioration. The concrete spalls, filling the vital gaps with grit and debris, until the heavily expanded slabs slam into each other and violently lock in place. Once a bridge loses its ability to slide horizontally, the entire span acts as a fully compressed, coiled spring. The massive thermal forces redirect backward into the rigid structural members. When those pressure valves fail, the invisible thermodynamic load stops moving across the deck and drives straight down into the foundational supports holding the bridge in the air. On continuous straight spans, these unrestrained thermal forces cause heavy precast concrete beams to warp upwards, a process known as hogging, cracking the underside of the structure. The geometry of skewed and curved bridges creates a deadlier reaction. The expanding deck shoves the entire multi-ton structure sideways, driving it directly against its own base. That resulting sideways shear force is powerful enough to snap solid concrete piers, tearing the bridge clean off its foundation. We have spent the last century building massive monuments designed to defeat gravity, but the Earth is hotter, the materials are exhausted, and modern engineering is now fighting a losing battle against the immutable laws of thermodynamics.